Okay, so black holes, right. Everyone loves black holes. But today we're not talking about just your average run-of-the-mill black hole.
Right. We're going deep on some fascinating new research you sent over that really shakes things up.
It suggests that black holes, the ones we think we know, they might actually be part of something much, much bigger, like a whole network of extra dimensions.
Yeah, it's a pretty mind-bending idea.
Science fiction stuff, almost.
But that's the amazing thing. It's not science fiction. It's actually grounded in solid math.
And it could solve some big, like really big mysteries in physics.
Absolutely.
So help me out here, because this is where I need to catch up. Usually we think of black holes as like these points of infinite density, right? Singularities, where all the normal rules of physics just kind of break down. But this research, this is saying something different.
Yeah, it kind of throws a wrench in that whole singularity picture.
Yeah.
The basic idea here is that our four-dimensional space-time, the three dimensions of space plus time, it's maybe not the whole story. It could actually be just a small part of a much larger, higher dimensional structure.
Hold on, hold on. So you're saying like there are more dimensions than the ones we can see?
Exactly.
Yeah.
Imagine like if you project a 3D object onto a 2D surface, like a shadow, right?
Okay, yeah.
You lose some information, right? You can't tell how deep it is from just the shadow.
Right, right.
But the original object, the 3D one, it still have all that information.
So our universe, it's like a shadow of something bigger. And black holes, are they like the points where we can see through to the other side?
That's a great way to put it. The research uses this idea of fiber bundles to describe this higher dimensional structure. So think of our normal space-time, the one we know and love, as the base of this bundle.
The base, okay.
And then attached to each point, there are these extra dimensions, like tiny invisible fibers.
Fibers.
And all these fibers together, they make up this bigger, higher dimensional space.
Okay, I'm trying to picture this. So we got these fiber bundles, these extra dimensions. But how does that change what a black hole actually is?
Well, instead of just a single point, a singularity, you might actually have multiple horizon surfaces. And gravity, the way it works near a black hole, gets seriously weird.
Okay, that makes sense. More dimensions, weirder gravity.
Yeah.
But then they talk about this fiber charge thing. What is that exactly?
Yeah, it's a new idea that comes out of this framework.
It's not like the charges we already know about, right? Like electric charge.
You get a whole different ball game. Think of it like this. Electric charge, it tells you how a particle interacts with the electromagnetic field.
Right.
Fiber charge, it tells you how the black hole interacts with these extra dimensions, those fibers we were talking about. It's all tied up with the geometry of these higher spaces.
Okay, so this is already getting pretty complex. Extra dimensions, fiber bundles, fiber charts. Like we're rewriting the rules of physics here.
Yeah.
But you said earlier that this whole idea could actually solve some mysteries about black holes. Like what? Give me an example.
We'll take the information paradox. One of the fundamental things in quantum mechanics is that information can't just disappear. It can change forms, but it's always there somewhere.
Right, that's the law.
But then black holes come along, and they're supposed to crush everything down into a singularity.
Yeah.
So where does the information go?
Yeah, that's the paradox. It's got to go somewhere. So how do extra dimensions help with that?
Maybe, instead of being destroyed, the information gets encoded in the structure of these extra dimensions, those fiber bundles. Remember that shadow analogy?
Right. The 3D object still has the info even though the shadow doesn't.
Exactly. So maybe the information that falls into a black hole doesn't disappear. It just gets, like, translated into a different form.
It's hidden in those extra dimensions.
Oh, sure.
That's pretty wild.
Is one way to make those two ideas play nice, the crushing gravity of black holes and the laws of quantum mechanics.
So that's one paradox down. But what about the firewall paradox? Doesn't that mean the edge of a black hole is like this super hot, fiery wall of energy?
Ah, yes. The firewall paradox. That's a tricky one. It comes from trying to make Einstein's general relativity work with quantum mechanics near the edge of a black hole, the event horizon.
And it says that basically anything that crosses the event horizon gets fried.
Pretty much. Instant incineration. But again, this new framework with the extra dimensions, it throws a new wrinkle in there.
So how do these extra dimensions cool down the firewall? Do they act like some kind of cosmic fire extinguisher?
Maybe not cool it down, but they might smooth it out.
Okay.
It all comes down to entanglement. That's where particles are linked together, even if they're really far apart.
Right. Spooky action at a distance.
Exactly. And this framework suggests that particles inside and outside the black hole could be entangled across those extra dimensions. And that entanglement, it might actually prevent the firewall from forming in the first place.
Okay, so we've got information potentially hiding in extra dimensions, and maybe a way to get around the firewall problem. This is getting really interesting, but it's all still pretty theoretical. Is there any way to actually test these ideas, to see if these extra dimensions really exist?
That's the most exciting part. This framework isn't just a bunch of ideas. It actually makes predictions that we can test.
Okay, but how do you test something that's like in another dimension?
We might not be able to see them directly, but we could see how they affect things we can measure. Things like gravitational waves and black hole shadows.
Gravitational waves, those ripples in space-time that LEGO and Virgo detect, and black hole shadows, like that picture from the Event Horizon Telescope.
Exactly. The extra dimensions, they would change those things in very specific ways.
So you're saying we could actually see the effects of the extra dimensions even if we can't see the dimensions themselves?
Exactly. For example, with gravitational waves, we might see these echoes in the signal.
Echoes, like the waves bouncing off the extra dimensions.
Well, not exactly bouncing, but the interaction with the higher dimensional structure would leave a mark on the waves, something our instruments might be able to detect.
So it's like we're listening for echoes from another dimension. And what about the black hole shadows? How would those be affected?
They could be distorted, their shape, their size, even how their light is polarized, all because of those extra dimensions. It's like a shadow puppet. The shadow tells you something about the shape of the object, even if you can't see the object directly.
So we're looking for distortions in the shadow to tell us about these hidden dimensions. It's like a whole new era of black hole astronomy is opening up.
Exactly. And there are even more ways to test this. Researchers are exploring the idea of creating mini black holes, or at least things that act like them, in laboratories here on Earth.
Wait, mini black holes in a lab? How is that even possible?
They're using these supercooled systems, things like Bose-Einstein condensates and superconducting circuits. It's still very early days, but the idea is that we could simulate some of the weird physics of black holes in a controlled environment.
So we're not actually creating mini black holes that are going to swallow the Earth, right?
No, no, nothing like that. These are just analogs, systems that behave in similar ways. But it's a way to test some of these mind-blowing predictions in a more controlled setting.
Okay, that's a relief. So we've got multiple ways to test this. Gravitational waves, black hole shadows, even lab experiments. This is getting really exciting.
We're just scratching the surface of what this framework could reveal about the universe. It's not just about black holes anymore. It's about rethinking our whole understanding of reality itself.
That's a great place to leave it for now. We've laid the groundwork, but there's so much more to explore.
Indeed. Next time, we can dig deeper into how this framework connects with other big ideas in physics, like string theory and loop quantum gravity, and what it all means for our understanding of, well, everything. So we've got this new framework, right?
Right.
And it's basically telling us that black holes are way more complicated than we thought.
Definitely not your garden variety black holes.
Not even close.
Yeah.
And the really wild part is how this all ties in with some of the other big ideas in physics, like string theory and loop quantum gravity.
Right, those are the ones that are always trying to unify everything, right? Quantum mechanics and general relativity.
Exactly. The holy grail of physics, a theory of everything.
And I remember hearing that those theories, they also talk about extra dimensions, but weren't those supposed to be like super tiny, curled up at the Planck scale?
Yeah, that's the typical picture.
So how does that fit with these like massive fiber bundles we've been discussing? Those seem pretty big.
It's a great question, and that's where things get really interesting. This new framework, it doesn't actually say anything about the size or the shape of the extra dimensions.
So they could be big or small.
Could be either.
Okay.
It just says they exist and then looks at how they would change things, especially black holes.
So these fiber bundles, are you saying they could be the same thing as those tiny curled up dimensions from string theory? Or maybe the quantum geometry stuff from loop quantum gravity?
It's possible. It could be that this framework is giving us a bigger picture,
Okay.
a more general way to think about higher dimensions that includes those other theories as special cases.
I see. So it's like this framework is a bridge between those super abstract theories about higher dimensions and things we can actually see in the universe, like black holes and gravitational waves.
That's a great analogy. It connects the dots between all these different ideas.
And maybe helps us get closer to a unified theory of physics.
Exactly.
Okay, but let's step back for a second. If this is true, if our universe really is just a projection of some higher dimensional reality, what does that even mean? Does it change how we think about everything? Like literally everything?
It definitely challenges some of our most basic assumptions about the universe, about space and time, even about cause and effect.
Give me an example.
Well, take information, for instance. If this framework is right, and information can be encoded in those extra dimensions, it makes you wonder, what is information anyway?
Right. I mean, we usually think about information like it's something we create. Like data on a computer or words on a page.
But what if it's something more fundamental than that?
Okay, so not just ones and zeros. What then?
What if information is woven into the fabric of the universe itself? Like it's just as fundamental as space and time.
Whoa, hold on. So you're saying information isn't something we made up. It's like baked into the universe from the beginning.
That's one of the big implications of this framework. It changes how we think about the universe itself.
So instead of just being a bunch of stuff like particles and forces, the universe is what, like a giant information network?
In a sense, yeah.
And it's all connected through these higher dimensions? That is a huge shift in perspective.
It makes you rethink a lot of things.
Like what?
Well, take locality, for example.
Yeah.
That's the idea that things can only interact directly with their immediate surroundings.
Okay.
But if everything is connected through those extra dimensions, then maybe that's not true anymore.
So things could interact instantly, even if they're light years apart.
It's a possibility. And that could explain a lot of weird quantum stuff, like entanglement, where particles are linked together no matter how far apart they are.
Right, spooky action at a distance.
Maybe those connections aren't so spooky after all. Maybe it's the extra dimensions that are making it happen.
It's like we've been looking at the universe through a tiny little window.
Yeah.
And now, with this framework, that window is suddenly opening up into this huge panoramic view.
Exactly. It's a new perspective.
And a new perspective can change everything.
It definitely opens up new ways to think about some of the biggest mysteries in physics, like dark matter and dark energy.
We've been trying to find those things for decades.
And coming up empty.
Exactly. But what if we've been looking in the wrong place all along?
It's possible. What if dark matter and dark energy aren't some exotic particles or fields, but just something coming from those extra dimensions? Something we can't see directly because we're stuck in our four-dimensional world?
It's like we've been trying to solve a 3D puzzle with 2D pieces.
Good analogy.
This framework is telling us we need to think bigger.
Literally.
So instead of building bigger and better detectors to find these particles, maybe we should be focusing on understanding the geometry of these extra dimensions.
Exactly. See if they can explain the effects we attribute to dark matter and dark energy.
It's a whole new way to think about the problem. But it still raises the question, where did those extra dimensions come from in the first place?
That's the million-dollar question.
And how come we can't see them?
We don't have all the answers yet, and that's what makes this research so exciting. It's not the end of the story, it's just the beginning.
It's a reminder that science is a journey, not a destination.
Exactly.
But we've got this new framework to guide us, and it's already leading to some amazing possibilities.
It is.
So we've talked about the theoretical side of things, all these big ideas.
Right.
But what about the practical side? How do we actually prove these extra dimensions exist?
The researchers who wrote this paper, they've actually outlined a plan for that. And it all comes down to those things we were talking about before, gravitational waves and black hole shadows.
Right, the stuff we can actually measure.
For the gravitational waves, we need even better detectors than we have now, like LIGO and Virgo, but more sensitive.
So we can catch those echoes.
Exactly. And for black hole shadows, we need better pictures, even sharper than the one from the Event Horizon Telescope. That way we can analyze the shape and polarization of the shadows really carefully.
Looking for those distortions that tell us about the extra dimensions.
Exactly.
And we talked about those lab experiments too, right?
Oh yeah, those are exciting.
Where they're trying to simulate black holes here on Earth.
It's like creating a mini universe in the lab.
Exactly. So we could have multiple lines of evidence from space and from the lab, all pointing to the same thing.
It would be pretty convincing.
It feels like we're on the verge of something really big here. This framework, with those extra dimensions, it has the potential to rewrite our understanding of reality.
It does. But it also raises a whole new set of questions.
Yeah.
Like, what does it all mean for us? For humans living in this four-dimensional world?
That's a good question. I mean, if these extra dimensions are real, could they affect us in any way?
Let's explore that next.
So we've gone pretty deep into this new framework. Extra dimensions, fiber bundles, all that mind-bending stuff. But let's bring it back down to Earth for a minute.
Okay.
What does it all mean for us, regular people living in our normal four-dimensional world?
It's a great question, and honestly, it's the most exciting part. Because even though this framework is super theoretical, The implications could be huge, even for our everyday lives.
All right, so let's play this out. Let's say we prove this is all true. Extra dimensions, fiber bundles, the whole 9 yards. What changes? How does that affect our lives? Our technology?
Well, for starters, it changes how we see the universe. It means there's so much more out there than we thought. Literally hidden dimensions all around us.
So it's not just like adding a couple of chapters to our physics textbooks. It's a whole new way of looking at reality.
Exactly. And that shift in perspective, it could lead to some pretty amazing technological advancements.
Okay, now you've got my attention. What are we talking about here? Like flying cars? Teleportation?
Think even bigger than that. What if we could manipulate those extra dimensions?
Manipulate them? How?
We don't know how yet. It's still early days. But imagine if we could. It could revolutionize everything. Communication, energy production, you name it.
Okay, slow down. Give me some specifics. How would extra dimensions change communication, for example?
Right now, all our communication relies on signals traveling through our three-dimensional space, limited by the speed of light.
Right, the ultimate speed limit.
But what if we could send signals through these extra dimensions?
So instead of sending radio waves or fiber optic cables, we'd be sending signals through, like, a higher dimensional shortcut.
Exactly. Instantaneous communication, no matter how far apart you are.
Whoa, hold on. That would be a game changer. We're talking about interstellar communication, instant connections across the galaxy.
Exactly. The possibilities are mind-blowing.
Okay, that's communication. What about energy? You said extra dimensions could revolutionize energy production. How so?
Well, think about it. If these extra dimensions are real, they're full of energy, all kinds of energy fluctuations we can't even imagine.
Okay.
And what if we could tap into that? It would be a whole new source of clean, sustainable energy.
So we could draw energy from the fabric of space-time itself.
It sounds crazy, right?
It does. But it's also kind of amazing. But let's not forget those big mysteries we're still trying to solve, dark matter, dark energy, all that stuff. Could this framework help us with those too?
It could. Remember how we were talking about maybe dark matter and dark energy aren't really particles or fields at all?
Right. Maybe they're just coming from those extra dimensions.
Exactly.
Yeah.
So if we can understand those extra dimensions better, maybe we can finally crack the code on dark matter and dark energy.
It's like a whole new approach to these problems. But with all this talk about amazing possibilities, about changing the world, I have to ask, are there any risks? I mean, messing with extra dimensions, it sounds kind of dangerous.
It's a good point, and it's something we need to think about very carefully. If we do learn to manipulate these extra dimensions, we have to do it responsibly.
It's like opening a door to a whole new realm, right?
Exactly. We need to be prepared for what we might find on the other side. We need to make sure we don't unleash something we can't control.
So it's a balancing act. The potential rewards are huge, but we need to proceed with caution.
Absolutely.
Well, this deep dive has been quite the journey. We've covered a lot of ground, from the mind-bending physics to the potential impact on our lives.
Yeah, it's been a good one.
And one thing is clear, this new framework, it's opening up a whole universe of possibilities.
It really is.
And to everyone listening out there, if you're as fascinated by this as we are, keep digging, keep asking questions, keep exploring. Because the universe, it's a pretty amazing place, and there's still so much left to discover.
Couldn't have said it better myself.
And that's it for the deep dive. Until next time, keep those minds curious and stay tuned for more fascinating journeys into the unknown.